saw yesterday these diagrams. The difficult point when lambda is different from 0 is to integrate that. You need to do it numerically. So, and this is also true in many cases. Like, for example, when we see the Secares models, you see that the same integral will appear. And so at that point, it's better to work numerically. Then we already saw yesterday the energy diagram, and you see the effect of the cosmological constant. The effect of the cosmological constant is to allow more degrees of freedom. For example, you can have a configuration that comes from infinity, from R infinity, reaches a certain finite R, and then bounces. These are stable configurations. These are also stable configurations, the ones that start in the Big Bang, bounce, and collapse. These are stable also. And these are stable, but the ones that come near here are very unstable. That means that if you have the exact value of the parameters, then you reach something that is analogous to the Einstein universe, but a little change in the parameters, it either collapses or expands. Now, in this diagram, because this equation is mathematically identical or very similar to the Friedman equation for FLRW dust. See? As I showed yesterday in the blackboard, the equations are very similar mathematically. So, but the difference is that here, in an LTV model, all these m, k are functions, right? This means that the layers have a similar but different evolution, right? You can say, in a sense, that when you have an LTV model, that each dust layer, when I say layer, I mean a two-sphere of dust that is expanding, and then you pile up all these spheres, and that's a good description of LTV models. Now, each one of these spheres individually evolves as a Friedman-Robertson-Walker model. Each one. But the next one will evolve as another FLRW model with different density. And this is how you have a collection of FLRW models that are piled up together. This is a good description of the LTV model. But you have the degree of liberty to choose how you pile up all these sections of an FLRW. You understand? Each two-sphere, which is a dust layer, behaves individually as a Friedman-Lemaitre-Robertson-Walker model. But the next one will also behave as such a model, but with different parameters, with different density, with different spatial curvature, and so on. And so you can pile them up in many ways. And this is the extra degrees of freedom that you have, right? So what would be the effect here? The effect here would be that, for example, you can have some dust layers that will do this, and some dust layers that will do this, right? In Friedman-Robertson-Walker, you can't, because your parameters are fixed, are constant. So an FLRW model will either do this, or will either do this. It would be one line only. Only one line that would be an FLRW model, right? But here, what we have is that each one of these lines is it's a dust layer with FLRW dynamics. But in an LTV model, you can have all these possible behaviors in the same model. In FLRW, you can't. FLRW model, you only have one line. Because the constants here, these are constants and are fixed. But in an LTV model or an LLTV model, you can have in the same model, you can have some dust layers that do this, others that do this, others doing this, others doing this, and others doing this in the same model, right? Okay, this is important to understand the difference between an LTB and an FLRW model, right? It will be even more clear once we use metric functions. These metric functions are not very good to compare with FLRW, so we are going to define new ones. Okay? Wow, sorry. This, okay. Now, the solution to the Friedman-Robertson-Walker quadrature, the Friedman-like, the Friedman-like equation is a quadrature. See, the solution of this equation is some integral here that we call f. This integral f will depend on big R and will depend on all the parameters, right? And it has this structure. It is the square root of R, and here is the square root of a cubic polynomial. Square root of cubic polynomial is an elliptic integral, right? But because you have the square root here, it is not a simple elliptic integral, but is the sum of a first kind elliptic integral and a third kind elliptic integral. So it's very complicated. You can work it out analytically, but it's very complicated, and you need to understand very well elliptic integrals. And so it's not worth doing it analytically, it's better to do it numerically. Now, once you have this integral, suppose by art of magic, we obtain this integral, right? We have it. It's there. Once we have it, how do you obtain the function r prime? See, we know what is r dot. We know what is r dot. So how do we find r prime? Notice that we need r prime because r prime appears in the metric, and it also appears in the density, and appears in many quantities. So we need to compute r prime. So once you have this, you differentiate. Remember that Big Bang time is a function of r. It's an integration constant, which, because it's a partial differential equation, the integration constant depends on r, right? So we differentiate both sides with respect to small r, with respect to the comoving coordinate. Because as this is a partial derivative of big R with respect to small r, right? Okay? So we differentiate both sides. We use the chain rule, differentiate this with respect to r prime, with respect to m prime, etc. And we simply manipulate these numbers, and we obtain this quadrature, this result. See, but notice that to obtain this result, we need f. We need f, right? We need it. Otherwise, we can't do it analytically. Because, and now here I'm using this fact. See, in the general case, we have to do this numerically, right? In the general case. And here r dot comes because the derivative of r of f with respect to r, notice that this is f, and the integration variable is r, is big R. So this derivative will be the integrand, but the integrand is 1 over r dot. So this is how this formula comes about. Now, in the general case, lambda different from 0, we need to do it numerically. But for lambda equals 0, we obtain this. Because remember, I already showed you the analytic solutions, right? So in the case lambda equals 0, this f, this quadrature, is given in terms of elementary functions. Sines, cosines, hyperbolic sines, hyperbolic cosines. So you can do these derivatives explicitly, and this is what you obtain. This is a formula for r prime. Notice that r prime depends on the gradients of these functions, depends also on r, but r is already given in terms of parametric solutions. Do you remember these solutions? Or do you want me to write them in the blackboard? You remember them, yes or no? Say it.
No.
Yes or no?
No.
No. Okay. Well, the solutions had this form. In the case lambda equals 0, we are talking about this equation. Okay? And the solutions are might be there is absolute value of A. Okay. See, this is a parametric solution to this differential equation. Okay. Eta is a parameter that goes from eta has to be greater than 0. Eta equals 0 corresponds to Big Bang. If you set eta equals 0 here, then T equals T Big Bang, and you can show that R is 0. Okay? These are the hyperbolic models that expand perpetually, and their terminal velocity is positive. Okay? Now, this is one case, and another case is if K is greater than 0, then it's very similar, but with circular functions replacing the hyperbolic functions. Okay? See? Check exercise. Check that these are functions. There might be a factor of 2 that I'm missing here, but it's in the lectures that I'm going to give you the reason why I'm not giving you the copies is that, look, I don't want to give you some material that later we're not seeing. Yeah, suppose, see, the way the course is coming, it is not suitable for doing something rigid and giving it to you, because it depends on how you are understanding, right? So I changed my mind. I'm not going to, I have lots of material, but I'm choosing it as the course goes, right? Rather than giving you something that then later I will not see,
Okay.
and that will not, and then seeing things that are not contained in the material. So I prefer that we finish the lecture today, and then I organize what we saw, and then I give you afterwards the material. See? This is the way I'm going to proceed now, right? So, but anyway, these solutions will be, the exact formulae will be in the material that you have, okay? Okay, it will be, don't worry, these things will be in your notes, in the material. Meanwhile, you can copy them from the blackboard, okay? And a good exercise is to test. The exercise would be to test if these solutions solve this equation. Notice that we are not seeing the case k equals 0. The case k equals 0, what we have is that r, k equals 0, we have that r is proportional to t minus TBB to the 2/3. Right? I don't remember the exact form, but you can deduce it. It's easy to deduce. The case k equals 0 is very simple. I would like you to test this, okay? And then there are also some implicit forms, because this here, the solutions, when I say parametric, these are solutions of the form right? These are parametric solutions. You use one parameter to solve them, right? But you can also find an implicit solution of this form. This is an implicit solution of this equation. So what I'm giving you here are these two parametric solutions. But this, it is very simple to obtain, given these two solutions, to obtain this one. That's another good exercise. How do you do that? You eliminate eta from here, and you substitute it here, and then you get the implicit solution. Okay? Good night. Good night. Good night, everybody. Okay? Well, okay, given a choice of three parameters and the analytic expression for R, and notice that once you have this formula, you can substitute R and these two things, you can substitute them with this parametric form. And this is one way where you can actually compute things. Okay? And of course here you have R dot, which is this. You can also substitute R and R here from these parametric forms. Okay? I think it might even be a good exercise to do this type of substitutions in the blackboard. Right? Because, you know, for somebody who has done this type of substitutions 3,000 times, it's terribly obvious. But since you have never done them, so it might be helpful. We're going to do some substitutions here. Okay? See, this is the point. I prefer to go much slower, but that you actually understand these things, even if we see less material. But this is going to be the approach. We are going to see examples of this, and then we'll give you exercises as well. Okay? Okay, so given a choice of three parameters, M, K, TBB, and the analytic expressions for R and TBB, these analytic expressions here, and also using this form of R prime, right? Now we can compute all quantities we want. We're ready. Now, this is all you need in LTV models to compute quantities. That's it. This is why these models are so popular, because they are so simple. Which quantity? For example, we have two scalars. One scalar is the density, right? So how do you compute the density? M prime M, remember M is an input parameter. You supply M, right? So M, then R squared, computed from here, right? R prime, you computed from here, okay? I'm not saying it's going to be a small expression. It's going to be large. But it's analytic. It's analytic, yeah?
So to get R prime, you have to put value of F, no? In earlier equation.
Yes, to get R prime,
you have to use
you need to have an analytic expression for this quadrature.
Yeah, okay.
Which is possible here. In fact, here it is. See, here, where is the analytic expression for this quadrature? Is the implicit solution. The implicit solution, the chalks seem to have vanished in the blackboard. Okay. I had one, but I don't know where I put it. Here it is. Gosh. Okay. So, look. The quadrature F is simply this integral. It's simply a dr is this integral. From 0 to R. That's it. And this is going to be equal to T minus PVB. Right? To make it even more clear, this will be okay. So this is the quadrature. The implicit solution is the quadrature. Come on, folks. It's a partial differential equation. It's a partial differential equation. That's all. And it's a very simple partial differential equation because it has only a time derivative. And the only function that depends on time is big R. Okay? We'll do examples. Let me just continue here. We'll do some examples. I want you to go out today for tea and say, wow, I really understand these models. I really understand. I take a shower and these models are with me. I go to bed and they are. I have breakfast and here they are, and they are not threatening at all. They are very nice models. I understand everything about them. Okay? So we're going to do exercises on this. Okay? Now, we can compute the density. How? Because we know a formula for R prime, and so we can compute this. Okay? Now, there is another parameter that we're going to call H, and this is the expansion scalar divided by 3, and it has this form. Now here there is R dot. R dot, we get it from here, right? R dot over R is going to be 2/3 of this, but then the denominator will be R to the 3/2. Okay? And then here we have some horrible thing. R prime dot. How do we obtain R prime dot?
We have R prime from
There are several ways. We can either dot this thing.
Yeah.
If we dot these things, then remember these are functions of time, and there would be a dot here.
Yeah.
yes.
This is a function of R, and here we have the dot of t is 1. Okay? The dot of this is 0 because and here we would have double dot.
Yes.
But we get double dot by dotting this. And then we just substitute. Okay? So you can compute all these things. See? You can compute all these things. Notice that the Hubble scalar is the logarithmic, is the derivative of the logarithm of this quantity. Okay? Okay, so you can compute everything. So let's see an example. Let's see an example here in the blackboard of computing this. Eraser. Where is it?
Is there one board?
Ah, it's on the blackboard. Okay. Thank you. No, up to no. Neither. Too much enthusiasm. No, this we need. Okay, we need this. Well, so here we have R equals M, but I'm not going to repeat it, but R prime, let's write R prime. You dictate to me. R prime equals what?
Minus M prime upon minus KT upon K.
Multiply times,
R.
but R is
R is M by K and cos hyperbolic theta minus 1.
I'm going to say CH will be a parabolic cosine, okay? 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 What else?
Minus M prime by M minus 3 by 2 K prime by K.
Multiplying
T minus
T minus TBB.
okay?
Yes.
Then,
Minus T prime B.
minus T prime B.
yeah, T minus TBB is here. I
Yes.
already wrote it. Ah, TB prime.
Minus TBB prime.
And then it closes here.
Yes.
R dot.
R dot.
And then times R dot. But R dot, we have it there.
Yes. Root 2M
So-
minus KR.
It is going to be the square root of
2M minus
2m. Well, it is actually something like this, because remember that k is negative, right?
Yes.
K is negative here. Everywhere remember that k is negative. Okay? So, so multiplying r, right?
Yes.
But r is this. Okay? And then this is divided by
Square root.
the square root of r, which is square root of m, square root of k, square root of, so that's r prime. Notice that these are functions of r. See, functions that have to be specified are m, k, and tbb, right? Yeah? You can compute it. The question is, now somebody tells me, well, if I choose m to be the logarithm of the second of the tangent of hyperbolic or whatever Bessel function, or yeah, it's possible. We're talking about mathematically computing. We're still not saying there are physical choices for these parameters, but first I want you to understand the mathematics. It's computable, right? Okay? So now, how do we do this one, this fellow, prime dot? Well, prime dot, the simplest way is to dot the primes. It's easier to dot the prime. So what would be? It would be, let's see. But then you know that R dot, you already know that R dot is this. R dot is this. R dot is this. And then you substitute it. Right? You already know how to substitute. Right? And then what's next? Minus. Sorry, yes, it's this is going to be multiplied times 1. See? Because the derivative of t with respect to t is 1.
Yes, sir.
Right? And this will be multiplied times r double dot. But how do you find r double dot? Well, you dot this. And you substitute again. Yeah?
Yes.
That's it. That's it. You compute all this. Once you have all these things computed, and here we did it for the case of negative k, but the same can be done for the case of positive k. Right? And so here you can, in fact, you can even plot these things. If you invent yourself, if you want to invent yourself some functions, just be careful that k and m and k have to be 0 at the origin. And they, well, we'll see. You will know how to prescribe these functions. Meanwhile, if you just want to exercise mathematically and plotting them, you can plot them. In fact, Mathematica and Maple have the possibility of plotting. See, notice that we don't have. Is this correct? Is this understood?
Yes.
Do you realize that you can compute things with these models? Analytically, completely. Right? You can compute them analytically. Now, where is the blackboard? Lights went off. Magic doesn't work. So what happened with this light? You know what happened?
Yeah, it will come out.
Some ghost? Sorry?
Generator will start.
Generator. Magic work, but delayed. Delayed. Okay, so there is one important thing here to notice. Let me erase this thing here. So, what we have, again, I emphasize, we have solutions of this form. Have solutions of this form. We have solutions like this, right? It would be nice if we had solutions like this, right? Don't you agree?
Yes.
We don't have. Not possible. What we have is the implicit solution. Right? We have the implicit solution, but we don't have the explicit solution. We don't have the parametric form or the implicit solution. However, Maple and Mathematica allow you to plot the explicit solution, even if you don't have the analytic form. You can plot it.
Means in TNR.
Sorry?
In TNR.
DNR.
TNR, no? As a function of TNR.
Ah, yes, yes, yes. It's a function of TNR. You can plot it.
You can plot it if you
Even
don't
if-
have, yeah.
Yeah, how you plot them? Well, very easy. By plotting them parametrically. How many people are more familiar with Maple than Mathematica? And how many people are more familiar with Mathematica than Maple?
All I'm learning, I think.
Okay, so I don't know the instruction, the syntax in Mathematica, but I'm sure you can find it. The instruction to do this in Maple,
Sir,
yeah,
the equations for R and T, they seem very similar to be that for cycloidal motion.
the one for what?
Cycloidal motion.
Cycloidal, yes, yes, they are. They are similar. Yeah, that's true. See the instruction in Maple. Suppose you have this t as a function of eta and r as a function of eta and r. Suppose you have this, then in Maple you would do this: plot 3D, and then here you would put your function t of eta and r. Here you would put r, and here r of eta and r. And then the following part is the syntax. Is you have to say r goes from 0 to, let's say, 2, and eta goes from 0 to, I don't know, 3, whatever. And then here are the, if you do this, what you will get is a plot in which t appears in the x coordinate, r appears in the y coordinate, and z appears, and r appears in the z coordinate. So it is really a plot. It's a plot. You would see r. The plot will show you r as a function of tr. Big R as a function of tr. Okay? In fact, I have an old paper that I think you should download because it shows how to do all these calculations. This paper I published in 2002, and
It is
sorry?
open access, sir.
Sorry,
Your paper is open access,
what?
available free on net.
Archives. It's an archive.
It's in archives, yes.
Archive. Okay.
If you look for me, you look for a paper, my paper's in 2002. It's one paper I published with a student called Garcia Trujillo. Well, I think that it is the only paper I published in that year on LTV models. And you recognize Garcia Trujillo, Trujillo,
How do you spell Trujillo?
Trujillo with J, Trujillo.
J-I?
Yeah, it's the other author. You see this. That's the name of the other author.
Trujillo.
Trujillo, would say. Trujillo. Okay. That paper has a lot of has examples of these computations, but that paper is using a parametrization of the models that we will see very soon now. This paper, see? That paper uses. I have to change the metric functions. There is a way. You can change the metric functions so that they look like FLRW functions. And this is a more friendly parametrization. All these calculations are still valid with them, but they are easier to understand. Okay? And my paper with Trujillo uses this new parametrization. But meanwhile, yeah,
In this plot, you are declaring two variables, R and eta.
yeah,
Okay. And the capital R is a function of eta and R.
yes.
Okay.
Yeah, it's a parametric solution. It's a parametric solution. Eta is a parameter.
Yeah.
Okay?
What about? And which type of graph it would be? Means I don't know.
Do it in Maple. The best way to understand is to do it.
Yeah.
Otherwise, sounds like magic. Okay? Well, now let's see the next thing here. We also have, remember, two space-like symmetric trace-free tensors. These tensors have this form. This is the shear tensor, which is proportional to this tensor AAB, the electric Weil tensor. And this thing here, this tensor here is diagonal minus 2, 1, 1. You've already seen that. Yeah, you remember that? You've seen this, okay? Now this unit vector n satisfies, it is a normal, it is a space-like, unit space-like vector that is orthogonal, is orthogonal to the 4 velocity. And it would be also, it is also orthogonal to the orbits of the group, to the spheres, the layers. So it's orthogonal. Okay? The eigenvalues of these tensors are the scalars we need to compute. See? These scalars, sigma, capital sigma, and psi2, are eigenvalues of these tensors with respect to this frame. In fact, this is a unique eigenvalue because this tensor satisfies certain covariant properties, like its divergence is 0, its covariant derivatives of this tensor are 0. So anyway, the thing is you have to compute sigma, big sigma, and psi2. And these quantities are given in this form. See, this is, now you know how to compute r dot and r. You also know how to compute r dot prime and r prime, right? So you can compute all this. And then this is n divided by r cubed, and this is rho, which also you already know how to compute. So you can compute these quantities as well. Now, there are 4 scalars that how do you know that you are already able to compute everything in LTV models? Because the models are characterized by 4 covariant scalars. The density, the Hubble scalar, the psi2 scalar, and the big sigma scalar. Because these are the 2 basic covariant objects of the models are density, expansion scalar, shear tensor, and electric Weil tensor. So this is what we saw in the previous lectures. If you write these models in terms of the 1+3 formalism, Einstein equations reduce to evolution equations for these 4 scalars and constraints. So once you know these 4 scalars, it is equivalent to having fully solved Einstein equations. Now, you see there how you can compute all these scalars. So these scalars are determined. Is this understood? See? How do we know that we have really solved Einstein equations? because we can compute these four scalars completely. We can compute them completely. Given three functions, m, k, and TVB, we can fully compute all these covariant quantities. That's the models have been completely determined. There is nothing in these models we cannot compute. Okay? And of course, we can already start computing like this. But there are other ways to deal with the models. As we will see, with the 1+3 system, we can look at the models as a dynamical system. That's another possibility. But meanwhile, we can compute everything analytically. Okay? Okay. These derivatives, notice that the derivatives r prime, r dot, and this is r dot over r. And this is r dot prime over r prime. These derivatives appear here, they appear here, and they appear here. Now these derivatives, we can also define them in terms of the covariant scalars. Like by definition of H, not definition, by computation of H is computed. By computation of H, why is it computed? Because we do this divergence. We compute this divergence. And the result is this. It's not that I define them or invent it. It is a computation. We have a four velocity, and we have a metric, therefore we compute this covariant derivative. And the result is this. And the same here, the same thing here. How we compute sigma? Well, there is a formula for sigma in terms of covariant derivatives. And we compute it and we obtain this. I showed you this for the Kantowski-Sachs. I need to show you this also for LTV models. That's a Maple worksheet that I'm going to show after the lunch break. Okay? I mean after the tea break. Okay, so notice that these derivatives can be expressed in terms of H and sigma also. So in these derivatives have a covariant meaning. They are this sum and this subtraction of these two quantities, right? They have covariant meaning, okay? What is covariant? Meaning coordinate independent, right? If you are in a spaceship and you don't know what coordinates you are, but somehow you can compute the shear tensor, they tell you this is a four velocity in the coordinates of the planet Vulcano. So doesn't matter which coordinates are, very strange, you compute the shear. And then you compute the Hubble scalar, and you do this algebraic combination and you recover these quantities, even if you are in a spaceship with strange coordinates, right? This is the idea of covariant quantities, right? That you can compute them in any coordinate system, and you will get the tensorial relations. Okay? So, the curvature tensors, we can compute these quantities now. The curvature tensor, R, is the Ricci scalar. And the Weyl tensor, it's expressible in terms of the electric Weyl tensor. And therefore, all curvature scalars are expressible in terms of the density and the scalar psi2. I've shown you before transparencies which show how the Weyl tensor decomposes in terms of the electric Weyl tensor, right? And how the Riemann tensor decomposes in terms of the Ricci tensor, the Ricci scalar, and the Weyl tensor. So you can compute these tensors as well. It might be time consuming and complicated and so on, but you can do it, right? So there is a big difference between knowing the algorithms, knowing what you have to compute, even if it's a mountain of work, but you know how to compute, right? So it's really donkey's work, because you already know what to compute, so you need a very good donkey to do it, right? That's a very different thing from having to calculate something that might be easy, but you don't know what you have to calculate. This, the donkey cannot do. Well, maybe some very, very special donkeys, but for that purpose you need a person thinking, right? Okay? Well, wow, this thing. Give me some minutes to work this thing out. It shouldn't appear like this. Let me fix this, because let me fix this. Give me 1 minute, okay? Because I really would like to. Meanwhile, you can take a very quick break, but make it a very short break, okay?
किसके पास है भी?
Parameterize the metric function so that the whole thing looks more like an FLRW. Not going to be identical, but the fact that the metric functions look alike facilitates a comparison between them. And that's interesting because LTV models can be conceived as a sort of exact perturbation of an FLRW model. It's not a standard perturbation, because when you say the word perturbation, people assume it's an approximation. And here there's no approximation, everything is exact. Okay? So, this is useful for applications to cosmology, because the metric and the metric functions look like their equivalents in FLRW. The metric parametrization is as follows. So, what?
So you are not connected.
Cable
is not
Ah, yes. You're absolutely right. See? So I was saying that you need a donkey to do this. Should be there. Okay, so we are going to express the metric in this form. Well, first, this is an FLRW model, right? We want the metric, we want to obtain a metric that looks like this. It's going to be the LTV metric, but in a way that it looks like this. So first we want to see what we want it to look like, right? This is an FLRW model. We're going to use the overbar to denote FLRW quantities. FLRW quantities depend only on time, and they will have a bar on top, right? So the scale factor, we're going to use this form of the FLRW metric. Remember that FLRW has several forms, right? We're going to use this one. Why? Because we want. It's equivalent. Doesn't matter. You are not forced to use. Coordinates are our slaves. You want a slave to carry, to make coffee. You have one slave that does it. You have a slave to clean the floor. So they say, hey, you want to have coffee, why don't you take the slave that cleans the floor? You say, because I have a slave that's trained to do coffee. So it's my will to follow this. Right? So, well, in Mexico, the union, the other slave will call the union, and he says it's violating human rights, and they will make a strike, and they could force you to use a slave that you don't need. Well, yeah, it's a joke. But here in GR, we don't have this type of demagogic unions, right? So you can use the coordinates that you want. Coordinates are your slaves. So you use them, and nobody from the union will come and say, hey, I am representative of the rectangular coordinates, and you have to use me. We don't have this problem here. So we use the coordinates that we want, okay? So this is R. Notice that the coordinates themselves are the same. We're just changing the metric function. But the coordinates are going to be the same. Now, once we have this metric, we already know that the Friedman equation takes this form, right? We've seen that. And it can take this nicer form in terms of the omega parameters. We've seen that also, okay? Right? Now, we want to get the LTV metric looking like this, okay? So the standard metric, standard LTV metric is this form, where the equivalent of this equation is this thing here, right? This is the equivalent. So we want to transform this so that it looks like this, okay? This is a LTV metric that we've been working for so far. And it is the LTV metric in its original and standard variables. See, lots of people, I would say the majority of people still use this representation. But there is a number of people who have used the one that I'm going to show you. Now, we do the following identification. We define a scale factor A without bar, not bar, so it is we reparameterize this metric by choosing first we choose a radial coordinate so that big R evaluated at some time, it's a fixed time, arbitrary, you can take it as present cosmic time, but it's an arbitrary fixed time. So this is very important. We make this coordinate choice. The radial coordinate is at our disposal. We can change the radial coordinate. We can relabel the... In fact, let me show you why we can do that. This is also important. It's this type of questions that once it's understood, you never need to ask again. See? This is the metric of an LTV model in the standard representation. This thing, to make things quick, this is the metric of the two-sphere, right? See, this thing. Okay? Now, this is a metric. So suppose we change the coordinate, we make this change. Okay? An arbitrary. Well, arbitrary as long as it's monotonic. It has to be a monotonic function. Okay? But otherwise it's arbitrary. Okay? Why monotonic? Because we want to do a map from R to R tilde, such that for every R, we have a single value of R, right? It has to be a monotonic function. Or in another way, if we plot r tilde as a function of r, we want something like this. We don't want something like this, because this means that for the same value of r tilde, we would get two values of r. We don't want. It has to be a 1-1 map, okay? Monotonic and smooth. Of course it has to be smooth. We don't want something like this, right?
It's continuous, no critical points.
Sorry?
It's a continuous function, no critical points.
No critical points, continuous, not only continuous, smooth. Okay? So suppose we do this. So then dr is going to be right? And then okay? So we put them all together. We put them all together here. This is the key here, right? We say this is right, but dr, because this map is invisible, then dr is going to be right, and this too, because of the theorem of the inverse function, this is 1. So you see, the metric doesn't change at all if we rescale the radial coordinate. If we rescale the radial coordinate, the metric remains the same. That means we have absolute liberty to rescale the radial coordinate as long as the rescaling is a 1-1 map, a smooth 1-1 map. That's important because some people in the literature, they make the rescaling, but it's wrong because it's not a 1-1 map. Okay? Is that correct? Understood? Okay? So, why I say that? Because we have the liberty of choosing or fixing the radial coordinate. And here we are already using it. What we're saying is that we are choosing the radial coordinate in such a way that r is a function of t and r. We evaluate this for a fixed value of t. Therefore, what we obtain is a function of r, right? But that function of r can be anything. It could be hyperbolic cosine of the logarithm of the tangent raised to the 7th power. It can be anything. Whatever that anything is, we say that's going to be our radial coordinate. See? We're going to say that this is, in a sense, what we're doing is this. We're defining our new coordinate by this condition. And then we remove the tilde on top. See? And this is what we're doing. We're using this degree of freedom now. Before, we had not used it. And this is one of the reasons why only 2 of the 3, you know, how many free functions we had? 3, right? M, K, T, B, B. But we can always take one of these functions and use it as a radial coordinate. So essentially, we have, strictly speaking, only 2 degrees of freedom. But that doesn't mean we have to use, see, that doesn't mean we can leave this coordinate choice unused. See, we don't have to use it. We have the chance to use it. But we're not forced to. See? Now, sometimes it's convenient to do it. Now it's going to be convenient, and this is the choice that we're going to take. See? This is an important choice because R, do you remember what's the physical interpretation of big R?
Radius of the two.
The radius of the orbit, right? Is, or the square root of the area of the orbits, right? The orbits are 2 spheres. Area of these 2 spheres is R squared, big R squared, right? Take the square root and you get a distance, right? So it's called the area distance, right? It's the area distance. So what we are saying is that our radial coordinate will be the area distance of our initial surface. So T0 is like your initial surface where you're going to put the initial data. And this choice means that we're choosing our radial coordinate to be the area distance along that surface. You realize it makes sense, right? Because the area distance has very clear geometric meaning, even physical meaning, right? You estimate, for example, when you are looking at a supernovae, you can estimate the area distance of that supernovae, right? Okay. And also, it makes geometric sense to choose the coordinate in this way. So we're going to choose it in this way, right? Second thing, once we've chosen this coordinate, once we have made this coordinate choice, then we define this factor, this scale factor, as the quotient of R with respect to R0. This makes, you remember, R has units of length. R0 has units of length. Therefore, A is dimensionless. Just like this A here is dimensionless, we make a dimensionless scale factor. However, bear in mind that it's not the same. Here is a function of time. This is a function of time and radius. Then we're also going to make this change. K is going to be equal to some kappa of R multiplied times R squared, where R is already defined like this. And M will be 4 pi thirds times a function mu times R cubed, right? Here M is starting to look like a mass. And obviously this is starting to look like some sort of density. Okay? Because the mass would be, suppose this is some sort of average density or uniform density. Then the mass is density times volume. See? 4 pi by 3 multiplying R cubed looks like a volume, right? So it makes sense, but for the time being, it's just a mathematical parametrization. Okay? So now, once we have all this, the LTV metric takes this form. Compare this with this. This is the same. Instead of A bar, we have A. Then here we have something that is explained here. This gamma is essentially R prime affected by this parametrization. Now here what we have is something that is 1 plus RA prime times A. And notice that this quotient R prime over R is equal to A dot, R dot over R is identical to A dot over A, because the difference between R and A is a function that is independent of time. Therefore, the logarithmic derivative is the same. See? And then the Friedman equation associated to this, notice that gamma is 1 for Friedman-Roberts. How do you get from here to Friedman-Robertson-Walker? Well, if A becomes a function of t only, then A prime is 0. And gamma becomes 1, and you go back to FLRW. Okay? So, the Friedman equation that we can form by dotting A will have this form. This thing, if you do all these changes here, if you substitute all this here, you can show that this fellow here becomes identical to this one. And this one, we're not going to call it H, but H perp. It will be clear why H perp. Because what happened with the FLRW models is that between LTB and FLRW. In FLRW, we have only one scale factor, right? In LTB models, we strictly have two scale factors, or two time functions, R and R prime. They are different. They are related, but they are different. Here, we have two scale factors. We have A and gamma. The scale factor A has a Hubble's parameter that we're going to call H perp. And this one will have another Hubble parameter that we will call A parallel, H parallel. Okay. Now, notice that this thing is very similar to this one, right? Notice that initial density is similar to this function mu, and this constant curvature is similar to this function kappa. But right now we're just playing. This is just mathematics. But it's nice because there is an equivalence. So how do we obtain an FLRW model from this? Well, first, A has to go to time dependent only. Then kappa has to become a constant. And mu has to become a constant. If kappa, mu become constant, then A has to be time dependent. See, notice what happens with this equation if suddenly mu and kappa become constant. Then automatically A has to be time dependent, right? Because its derivative would not contain any R dependent functions. Therefore, it is a separable function. And well, anyway, you can check that if this is constant, it implies that A is time dependent. And then this whole metric and Friedman equation reduced to this one. So, what is making the difference between LTB and FLRW functions is the fact that our free parameters, which are now kappa and mu, are radial dependent, right? And this forces A to be also radial dependent, right? Otherwise, we get Friedman-Robertson-Walker. This will be clear as I go along, right? But as far as we are concerned now, this is a very nice way to write the LTV metric. Because all what we did was this. We're still in LTV models. We're just calling names like, what is your name?
Arpan.
Arpad?
Pan.
Arpan? So now you are going to be called Alfredo. Right? This meet Alfredo. It's the same person, just has a different name, right? But it's the same person. So Arpan might say, well, why should I need to be called Alfredo? Well, in some cases it can be convenient. Maybe it's in some situations it could be convenient that you are called Alfredo, right? There's no change, you are still the same person. And you can always go back to your original name. But in some cases, say, or this is bottle, well now I'm going to call this thing pecera. So here, take your pecera. So it's just a name, it might be convenient for some reasons. So all what we're doing now is to change the metric functions, to reparameterize them. It's a rather innocent game, but it's important because it looks like a Friedman-Robertson logarithm, right? Okay? And okay, so now, once we have done that, this suggests that we can somehow define omega parameters in a parallel way as we do it here, right? And then we can express the Friedman equation as H per equals initial H per. We can express it in a similar way as here, right? It looks like, it resembles the FLRW Friedman equation, right? Then, but notice, and I emphasize, that these quantities are not constants. Here, these things are constant. Okay. It's the density today, which is a constant in FLRW models. H0 is a constant. So all these are constants. But here they are not constants, they are functions of r. They change from point to point.
Yeah.
Okay? So this is a very nice parameterization. Now, comparison with FLRW. This is what we have. This is a new LTV metric, and this is the H per, right? This is just what I mentioned before, right? Okay, so. Now, notice the first thing, that H per is not H. Okay, it's not H, because we can also compute H. So we need to be careful with interpretation of this Friedman equation. It's in FLRW models, what is standing in the Friedman equation is H. Remember that H is a covariant object. It is the divergence of the forward velocity divided by 3. H perp is not that, right? So it looks like. So here we have one case in which I call him Alfredo, but he's not the same person as some Alfredo I know in Mexico. Have the same name, but they are different people, right? So I has to be careful. Even I call him Alfredo for convenience, but I have to remember that he's not the same Alfredo that is all there in Mexico, right? So has to be very careful on this. Now, we can identify two Hubble factors. One Hubble factor is going to be the logarithmic derivative of the scale factor here. But we have here another scale factor. So we call this scale factor H parallel, and H parallel is going to be this fellow here, which is identical to this derivative. So we can, rather than this horrible derivative, we have this very simple derivative. And so we can make this identification, but now we have to two scale factors. Now, how these scale factors, what's the covariant interpretation of these two scale factors? Because when we're juggling with coordinates, we can define some things, but we have to be certain how these quantities can be computed in any coordinate system, right? So that's why we need a covariant interpretation for them. Well, the covariant interpretation follows by relating these Hubble factors to the scale, to the scalars h and sigma. What is h? Covariant derivative of the four velocity. The divergence of the four velocity. Covariant divergence. What is sigma? Eigenvalue of the shear tensor. Sigma. But now what we can see is that h is really going to be the sum of these two. H is different from each one, but it's the sum of these two. And h can be expressed in this way. On the other hand, sigma is the negative of the h perp, right? So h parallel is h minus 2 sigma, and h perp is h plus sigma. And that's the covariant interpretation of these factors, right? So now you can compute them in any coordinate system. So in any coordinate system, as long as you have a four velocity, you take the divergence, and then you have h. You compute the shear and find its eigenvalues, and you have sigma. Okay. So this can be interpreted in a covariant way in this form. Okay. So this is just what I said, right? H and h per. Now looking at the metric is nice because you have one scale factor here, you have another scale factor here, and then you can relate these two scale factors to these covariant objects, but also remember that you can compute these scale factors by the formula that we have developed here. You can compute them, right? You can actually compute them for given them. Okay? Another nice interpretation is in terms of this tensor. This tensor is the covariant, the symmetrized covariant derivative of the four velocities. See, if we compute this thing, we obtain this is the expansion tensor. Yeah, question? And then the expansion tensor has this form. So we can see that h parallel and h perp are the eigenvalues of the expansion tensor. Right? Like a lot of astrophysicists, now, so is there any astrophysicists here? Because I'm going to make an insulting statement. Is there any astrophysicists here? Tell me in order to take a shield, going to throw, the person will have to throw rocks at me. No astrophysicists? No?
No, sir.
No, sir. Okay, so I can insult them. Now, a lot of astrophysicists use this parametrization. They don't give a damn about the covariant interpretation. They just want to calculate and fit observations and so on. They don't give a damn about that. And so these people are unfortunate if they have me as a referee, because I tell them what's a covariant. You have defined this. What's a covariant interpretation of this? A coordinate thing. And these astrophysicists get very angry. This arrogant mathematician, this theoretist, is making my life difficult when I am dealing with a real universe, not with mathematical entities and so on. And there we have the problem of the dogmatic empiricists. As long as they're computing things and fitting observations and so on, they are right ahead, they are discovering, and they are real scientists. So you have to fight that. Because in the short term, yeah, they'll get lots of papers published and lots of grants and so on. But in the long run, if you don't understand well the theory, you are going to be like the donkey, right? Do lots of very hard work that requires little intelligence. We shouldn't aim to be donkeys. We all have to do donkey work, right? I'm not saying, so even Einstein, all great geniuses, they had to do donkey work. But they knew that that's not enough. Never tons and tons and tons and tons of donkey work are going to replace 5 grams of intelligence. You need to look for them, right? Donkey work is unavoidable. But try in your scientific lifetimes to do also intelligent work, theoretical work, to understand the concepts and so on, okay? So this is one way of understanding that if you are going to use these models to fit observations and compute the 2 scale factors and so on, to understand that these factors do have a covariant interpretation, a theoretical interpretation. In a sense, what the expansion tensor is telling you is that you have some models, you have a space-time in which local elements are expanding, right? But notice that they are expanding at different rates in different directions, right? See, along this direction, what controls the expansion along this direction, what direction is this? It's the direction, the radial direction. The radial direction is a direction that is perpendicular to the 4 velocity and perpendicular to the orbits of the group, right? So along this direction, the expansion is controlled by H parallel, which we already know how to compute. And along these 2 other directions, the expansion is controlled by H purple, right? And this difference in expansion along different directions is what gives you the big difference with FLRW. Because what would happen in FLRW? All these 2 factors are the same. See, notice what happens in FLRW. In FLRW, gamma is 1. Therefore, this is 0. And therefore, this one is this one. So this is 0. Sigma is 0. So H perp is H. H perp is H. And H parallel is H. So this sigma goes to 0. And this is a diagonal tensor with a single eigenvalue. What is telling you a single eigenvalue? Expansion the same in all directions, right? At every point. At every point, expansion is the same in all directions. What's the difference with LTV? In one point, that you have different expansion in one direction than in the other 2 directions. It's an anisotropic expansion. And it's also inhomogeneous because it changes from point to point, right? We already saw that the same thing happens with Kantowski-Sachs and Bianchi-1 models, right? So this is the difference. And if you understand that difference, which is not, you know what I'm saying, it's a small thing, it's not so complicated to understand. But once you understand, you can do all the donkey work you want. Fantastic, good work, fitting observations and so on, but you already understand that, right? And it's important, okay? Now, well, this is exactly what I just said. Local expansion rate, it's different in the different principal directions. What are the principal directions? Well, the principal directions, we already know how to define directions in a covariant way. One direction is a 4 velocity, it's a time direction. Then we have orbits, the 2 spheres. Yeah, the 2 spheres, they define 2 directions. We have 2 vectors that are tangent to the 2 spheres. And then we have a third vector, which is orthogonal to the 4 velocity, and is also orthogonal to the other 2 vectors. See? This is what we are calling the radial direction. The radial direction is a tangent vector to space-like geodesics. space-like geodesics that are orthogonal to the four velocity, to the world lines of the observers, and the tangent vector to this space-like geodesics are also orthogonal to the orbits. So we can also define the directions in a covariant way, right? I hope this is now very, very well understood. And you know that this also applies to Bianchi models, to Kantowski-Sachs, right? And this also comes from what we have seen, the 1+3 formalism, etc. I hope that you are starting to see how everything fits together, right? Everything is consistent. You are getting some sort of picture, right? Well, now, another thing that is also helpful, this is sort of mathematical, but it is a sort of summary of what I said. The LTV metric can be expressed in terms of an orthonormal tetrad. Every space-time can be expressed in terms of an orthonormal tetrad. Here, what we do is that we construct some vectors which are not the same as coordinates. They are proportional to a given coordinate vector, but they are not the same. In these tetrads, for example, the idea of defining the tetrad is that given a metric, we define 4 vectors so that this contraction is going to be the same as the Minkowski metric. That's why they are called orthonormal tetrads, because each one of these vectors will be unit vector and will be orthonormal to each other. So we define, this is the Minkowski metric. Now, in the case of LTV metrics, the time-like vector can be the 4 velocity, right? We need 4 vectors. They are unit and orthonormal. One of them has to be time-like, the other 3 are space-like. So the first one is the 4 velocity. The second one is the tangent to the radial geodesics, right? And it's simply to make it unit vector, we multiply times 1 times the GRR up component. And the other 2 vectors are these ones. And if we choose these vectors like this, we get this satisfied. I'll show that in the blackboard in a minute, right? Once we define this orthonormal tetrad, then we can see that H per is expansion collapse in the direction of these 2 tetrad vectors, which are tangent to the orbits of the rotation group. And H parallel is expansion collapse in the radial direction, which, as I have mentioned several times before, these are tangent vectors to space-like geodesics, and it is orthogonal to these orbits. So all what I'm saying, that the directions that I'm telling you can also be expressed in terms of tetrad vectors, right? In terms of tetrads. Because the decomposition of space-times, of any space-times in this way, is unique up to rotations of the tetrads. So this is like the coronation. Now, is there any doubt, like what I wrote here before? I think it's important to see it in the blackboard. Where is it? Ah, it's hanging over. Okay. Yeah. With the diagonal metric, is very simple. See, we have this diagonal metric. Now, okay, we have this diagonal metric. Okay, so, and we have GAB is -1 R prime squared okay. Now I choose vectors. One vector that is going to be 0 vector A will be delta A T. The following vector, now I know this vector is unit vector, right? It's a 4 velocity, right? See? And I know that, we know that this thing is true. Right? We know this is true. Okay? Now the next one. See? So we already have the first vector going to be the 4 velocity. Now the next vector, we need a vector in this direction that is also unit vector, that is space-like. So the second vector has to satisfy this condition. So which vector satisfies this condition? So we want this vector also to be in this direction. So we want this vector to be, let's say, F, and we want this vector to be in the radial direction, right? Okay. So how do we find the proportionality factor? We find it by this condition. So we have G AB F squared equals 1, right? Okay? So this is equal to why? Because the delta is a policeman saying whatever you see A, change by R. Whatever you see B, change by, or I make you 0. Okay. So what is F? F is 1 over square root of GRR, which is the same as square root of GRR. Right? And we do the same for the other vectors. And this is how we construct the tetrad. Now, see? So we have E1, E0 is the 4 velocity is delta AT, right? Now we have E1 is going to be 1 divided by GRR. And then what's going to be the vector number 2? And the other one, the same, likewise. The other one, Okay? These are the tetrad vectors. So what do we do with them? See, we have E0, E0, A, E0, B, right? We do this sum. Zero, A, 1, etc. What do we get? If we get this 2 here, E0 component is 1. Hold on. Well, this is actually a matrix because we have not contracted it. So, what is the AB component here? This would be -1. The 0, 0. The 0, 0 part of this is -1. The 1, 1 part of this is what? Is 1. Hold on, let me see. What are we doing? No. So what do we do with this? We prove this. This, or the way it is written here. Yeah. We're going to show this expression. Or let's show that this expression A, C, we're going to show that this expression holds. Okay? So, what is eta 0, 0? So, eta 0, 0 will be this fellow here, but with index 0. See, it's E, C, 0, E, 0, E, G, C, D. But this is simply delta, C, D, delta, D, D, G, C, D. This is simply G, because -1, right? Okay. Now let's do the other one. Let's do, for example, what happens if we do something like this? If we do something like this, it will be 0 because the metric is diagonal. See, just let's see. This would be E, C, 0, E, D, 1, G, C, D, but this would be
T drive.
Yeah, just let me finish
Oh.
one more question.
No problem.
You see? Because the metric has no component TR. So this is 0. Now let's do it for the 1, 1. Okay. So what will happen is that you will reproduce the Minkowski metric. The 0, 0 component, and here I put, because this is tetra, these are not coordinates, but the 0, 0 components here with these brackets is -1. All the mixed components are 0 because the metric is diagonal. And the non-diagonal components are 1. See? Now, why is this important? Because here with spherical symmetry, with LTV models, we can still identify the directions with the orbits of a group. Because of spherical symmetry, we have a group acting on two-dimensional orbits, and this is in itself a covariant definition, right? The orbits of a group, two spheres. And then the directions orthogonal to the two spheres are space-like geodesics. And then the other direction is a four velocity. So strictly speaking, for LTV models, we don't have to go to tetras. But what if we are no longer working with LTV models? We have something that is non-spherically symmetric. Then we don't have any more orbits of a group. The directions are the space-like geodesics are not going to be aligned with a space coordinate or whatever. So in this case, we use tetrads. And then the directions of the expansion tensor can be referred to tetrads. We can say, yeah, we have expansion, one eigenvalue in the direction of the tetrad number 1, and then one expansion in the direction of the tetrad number 2 and number 3. So when there is no orbits, no group, no space-like geodesics, nothing like that, we can use the tetras to specify directions. This is why it's important.
And these directions are covariant.
Yeah, this is covariant because they are referred to an orthonormal tetrad. Now they're not unique because you can still rotate them, but in most cases they will be unique.
And covariant feature is very essential.
Yes,
Yeah.
yes. If you are in a spaceship and they are giving you strange coordinates and you're observing things, you compute these things in those strange coordinates. You know that you are doing something correct because you are referring, it doesn't matter in which coordinates you refer. You're going to say, yeah, well, the expansion takes this form in the coordinates that I construct, in the orthonormal tetrad that I constructed. Because you know that if you change coordinates, the orthonormal tetrads are still markers, are still going to be good markers, right? This is independent of the coordinates. If I would have had a very complicated metric, computing the tetrads is complicated. But nevertheless, the tetrad is the same. What I'm saying is that if you have other coordinates, your tetrads will be the same. The tetrad is an invariant thing. It's a covariant quantity, right? And so it's useful to know this. In LTV models, it's not strictly necessary because the models themselves have already too much symmetry, and they give you covariant indications. But if you are not working with spherical symmetry, then this is very useful. Okay, so tea break.